In this video, we're going to discuss non-ideal solutions for the first time and discuss Henry's law and what it predicts about non-ideal solutions. So most solutions are in fact non-ideal. They're not going to obey Raoult's law at all concentrations, at all mole fractions. You could have the following case where you have molecule A, which is much smaller in size than molecule B. So in general, if that's the case, there's a large discrepancy, then the solution won't behave ideally. And it can either be that, or if you have interactions between the different components in the solution, they're not approximately equal to the interactions between the same types of components in the solution. If A and B interacted in the same way that A and B do, then twice this interaction would equal this plus this, and there would be no net difference. And then the things like the enthalpy and volume of mixing would be zero. But for non-ideal solutions, that is not going to be the case. So if we have our pressure composition diagram, we have mole fraction of component 1 going from 0 to 1, from none of it to all of it, from left to right. If you're obeying Raoult's law, we have that nice purple curve there, which is just a linear interpolation between the vapor pressure of pure component 2 and the vapor pressure of pure component 1 as it switches in between those two extremes. But you can have what's called negative deviation, where the vapor pressure is below that. The vapor pressure of the solution is below ideal for the composition range. Or you could have positive deviation, where it's greater than. And that's reflective of what's occurring with the intermolecular interactions. For Raoult's law, they're the same. The different ones are equal to the same interactions. So that you get that nice curve there. If you have a positive deviation, that means that the interaction between components is not as strong as the interaction within them. And if you have negative deviation, it means that the interaction between components is stronger than the interactions that are within them. And that just acts to either lower or increase the vapor pressure, depending on how these interactions make it stronger or easier for a molecule to leave the surface and become vapor. And we could go through a series of different solutions like we have here. We have component 1 being the smallest molecule that I've shown here, and then it obeys Raoult's law with some molecule which is also very small. And then if we have a series of molecules which are larger and larger, you could imagine something like mixing a series of alcohols with water and then including more and more carbons on the chain as you go, effectively making this effective radius of the molecule bigger. The solution will behave more and more non-ideally as we get to solutions which are more and more non-ideal, because the two components are less and less like each other. Okay, so this leads us into our discussion of Henry's law, this type of non-ideal behavior at one end, and then the approach to ideal behavior at the other. So what we're going to have is that the vapor pressure of a component I in the solution of a single component is going to approach the mole fraction of I times the vapor pressure of pure I as the mole fraction of that component approaches 1. So if it becomes a pure solution, then the vapor pressure becomes the vapor pressure of the pure solution. And in the limit of you're getting pure component 1, the vapor pressure is obeying Raoult's law again. And this is a direct result of Raoult's law. So that came from Raoult's law for ideal solutions. The solution is going to behave ideally at very, very large mole fractions of one component for that given component. And in the other case, for our minor component here, if we have it almost pure component 1, that would be considered a solvent. And if we had a very, very small amount of component 2 would be what we would call a solute. So for our solute then, the vapor pressure of our solute is going to approach its mole fraction times a constant called the Henry's law constant for that component in that solution. and that's going to approach this value as the mole fraction of our solute approaches 0. And this is Henry's law. So Raoult's law says that the vapor pressure of a component is its mole fraction times the vapor pressure of its pure liquid. Henry's law says that the vapor pressure of a component is equal to its mole fraction times some constant called the Henry's law constant. So I'll write that down again just to hammer that point home, that this KHI is called the Henry's law constant for component I in whatever solution it's in. It would be solution dependent. And the value of this Henry's law constant, again, reflects the interactions between our molecules, between A and B. That's not the greatest B, but that's okay. So what happens in the case of Raoult's law? So as the mole fraction of a component approaches 1, let's say this component is A, what we're going to have is molecule A is going to be almost pure, so it's going to be surrounded primarily by molecules of itself. So it's going to interact with itself equally at pretty much all concentrations there, because it's going to see pretty much only itself. So Raoult's law is going to be obeyed because the solution is going to be fairly ideal from the perspective of component A, because component A only sees other molecules of component A. And then in the other case, as chi approaches 0, from the perspective of component A, it's probably one of the few component A molecules in there, and it's going to be surrounded entirely by component B. So, in fact, this vapor pressure of component A is going to be determined primarily by how it interacts with component B. And if it interacts with component B differently than it interacts with component A, then its interactions are going to be reflected by its Henry's law constant for interacting with B. And then its vapor pressure will be predicted by Henry's law instead of Raoult's law. So as we can probably tell here by that discussion, we have some limiting values for what the Henry's law constant is. KHI is going to equal the vapor pressure of the pure liquid for an ideal solution. So for an ideal solution, it's obeyed at Raoult's law is obeyed at all ends. It's obeyed at both ends of the spectrum. So Henry's law becomes Raoult's law in the limit that the Henry's law constant becomes the vapor pressure of that pure component. And if it's not, we can evaluate it by the slope of these types of first derivatives evaluated at 0 mole fraction here. You can see the slope of this curve, the tangent line to this curve at 0 mole fraction is what I've extrapolated out here. And this shows the derivative of these curves shows you the Henry's law constant for each of those individual solutions. So we have that we can determine the Henry's law constant if we have a pressure composition diagram. For that Henry's law constant is equal to the derivative, or I guess I should say partial derivative, because it's not the only thing that controls it. Partial derivative of the pressure, the vapor pressure of the solution, with respect to mole fraction of component I, and that is evaluated when the mole fraction of component I is 0.